Okay, welcome back. So next question we're going to do is this question 3 from your book on page 91. And it gives you ABCD is a square, ABCD. Prove that the triangles ADC and ABC are congruent. So ADC, this triangle, and ABC, this triangle, are congruent. In this case, actually, we could use any of SSS, SAS, ASA, and RHS to prove that these two triangles are congruent. You won't always be able to use all of them. Usually, you'll be able to use only one or two, or maybe even only one. But in this case, there are lots of ways of doing this. So I'm going to choose the first one, so the SSS, and we'll use that for a start and maybe talk about some of the other ones that you could have done. So since the triangles are ADC and ABC, I'm just going to write them down first again. So triangle ADC and triangle ABC. Here are my two triangles. And I said I'm going to use SSS. So the first thing I'm going to do is, for the triangle ADC, I'm going to say the side AD is equal in length to the side BC. So AD, and we must use this notation, is the length of the line segment AD is equal to the length of the line segment. So that's AD is equal to the length of the line segment BC. Or AB we could have said, but we'll go for BC for now. BC. And the reason they're equal is just because they're both sides in the same square. So we can just say sides of a square. And whoever's reading can take it that we know that the sides in the square are equal, and that's why they must be equal. The next thing then is we have our, we used AD, so next our side DC is equal in length to the side AB. So DC equal in length to the side AB. And again, because they're two sides of the square, the same square. Sides of the square. Okay, and finally, well, we've got this side AC, which is in this triangle, but also it's part of this triangle. So what we can say is that AC, since it is a side in this triangle, is equal to AC, which is a side in this triangle. And the language we normally use is we say it's a common side. It's common to both triangles. And obviously it has to be equal to itself. So since we've proven that a side is equal, a side is equal, a side is equal, then we can say that triangle ADC is congruent to triangle ABC, and in brackets we used side, 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 SSS. Now, just to talk for a second about what we could have done, side, angle, side, we could have said this side is equal to this side because of sides in the square, and this side is equal to this side because of sides in the square, and we could have said this angle is equal to this angle because the angles in the square are 90 degrees. So we could have said side, angle, side, side, angle, side. We could also have used angle, side, angle, a bit more difficult, I suppose, where we might have had to show that this was 45 degrees by saying that a bisector of a square creates two 45-degree angles. So we could have said 45 degree, 45 degree, 90 degree, 90 degree, and this side equal to this side because they're sides in the square, and we could have used angle, side, angle. Equally, RHS, by saying that there is a right angle, or all the angles in squares are right angles. This is a right angle and is equal to that. The hypotenuse is common to both of them, and one other side, this side, is equal to that side because the side's in the square. So we could have used any one of these in this case. Now, it's rare enough that you'd be able to prove it in 4 different ways, but in this case it was straightforward enough.